we're going to take a look at what's called the rational zeros test. This helps us figure out what we might try in synthetic division or evaluating a polynomial to find its zeros. And so here's a nice review of just the expanded form of a general nth degree polynomial. So if you've got the power of x to the n in the list, then you call the coefficient a sub n. And the next term, x to the n minus 1, would have the coefficient with the same subscript as it has power. So when you finally get down to the quadratic term, if any, power x to the second, you have a sub 2. And a sub 1 times the linear factor, and a naught is the constant for a general polynomial. So, okay, that's nice to look at again. So you let f be a polynomial function, and we're assuming that its coefficients are integers. So they're whole numbers and opposites. Then we would say this value, p over q, which is a rational number, is a zero of that function if the following two things are true. Well, it's a candidate to be a zero of this function if p is a factor of the constant term, so the top number divides the constant term evenly, and q is a factor of the leading coefficient, so q divides the leading coefficient evenly. So as long as the original polynomial has integer coefficients, all these coefficients are integers, then the zeros, or the candidates to be x-intercepts of the graph that are rational, would have these two features. Okay, a specific example from the textbook we're using right now, I guess they call it example 6 in the text. So we have this third degree polynomial, leading coefficient of a 2, constant term -3, and all of the coefficients for the polynomial are integers. -3, -4, 5, and 2. Our whole numbers are opposites. So if you're looking for candidates of things to try in synthetic division, to try to see if you have zeros, you're going to look at this constant right here in red and write down all of its possible factors. So 1 and -1 divide -3 evenly. 3 and -3 divide -3 evenly. And we list those, so there's 4 candidates as numerators. The leading coefficient 2 in blue has only 4 factors. 1 and -1, 2 and -2. Okay. And like that rational zeros test explained, we'll use the factors of the constant as numerators. Alright, so the possible rational zeros. If it has a positive 1 on top, we could put that over 1 or -1 or 2 or -2. So you see that they have put 1 and -1, 1/2 and -1/2 in the list. So that's if you use 1 as a numerator. Okay. If you use -1 as a numerator, you're going to get the same possibilities. -1 as a numerator. But then when you switch over and let 3 be a numerator, you're going to put 3 over 1, 3 over -1, 3 over 2, and 3 over -2. That's the scratch work. And we get 3 and -3 as a possible rational zero. 3/2 and -3/2, if I put the negative there, as rational zeros. And if we continue on and use -3 as a numerator, we're just going to have redundant possibilities. Okay, so that's how they showed on this slide to get a list of possible rational zeros for this particular quadratic up here. All right, let's start one from scratch, and let's see what we've got under here. Okay. Oh, this is one of the examples in the book. All right, so let's just see how this is done in practice. We've got a polynomial. Again, I used a third degree, but it has integer coefficients. What are they? 6, 13, an understood 1, and -2. The constant term was -2, and it has factors of 1 and -1, 2 and -2. Your publisher would have written plus minus 1, plus minus 2, just to be more compact. And then we move up here and we look for that leading coefficient 6, and it has several factors. 1 and -1, 2, -2, 3, -3, 6, -6. Does it have any more? I think that's a complete list of things that would divide evenly into 6. So our possible rational zeros, and these will correspond to possible factors of the polynomial, will be the fractions where we start with the number 1 in the numerator, and we put 1 over 1 and 1 over -1. So that's plus or minus 1. We put 1 over 2 and 1 over -2, plus or minus 1/2. We put, I'm still on this 1 over 3, 1 over -3. 1 over 6 and 1 over -6. Okay. And I really don't have to go through that process again because -1 over 1 is already in my list. -1 over -1 is also in my list. -1 over 2 is here in the list, and so I've really gotten those for free. Now I need to take this number and put over each of these denominators. And 2 over 1 is not in the list yet. And 2 over -1 would be the opposite of 2. 2 over 2, however, reduces to 1 and is in the list. 2 over -2 reduces to -1 and is already down here in our list. But 2 over 3 is not in the list, or its opposite. 2 over 6, that would reduce to 1/3. So 2 over 6 is already in our list. That takes care of that one. And if we look again, this fourth numerator, putting it over each of these possible denominators, those options are already in the list. So that option's done. 1, 2, 3, 4, 5, 6 times 2, 12 possibilities for zeros. When we do our synthetic division, we don't need to try anything else but those rational possibilities. Okay, you could stop the video here, or we can talk about how to use that list to actually go ahead and factor this polynomial. And I'm going to write out those possibilities again. I've got my whole numbers here and here, and then there's a bunch of fractions, aren't there? Plus or minus 1/2, plus or minus 1/3, plus or minus 1/6, and plus or minus 2/3. Okay, these are possibilities. Okay, to get started in factoring, we're going to use our factor theorem, and we're going to evaluate f for some of these simple values here. So let's evaluate f at +1. So I'm going to plug in a 1 here, 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 and I'll get 6 times 1 plus 13 times 1 plus 1 minus 2. That's 18. That's not 0. So I don't need to worry about doing synthetic division with the 1. Okay. Let's try the next easiest number to plug in. Let's plug in a -1. And anywhere I have an odd power, I'm going to get a negative product. So I'm going to get 6 times -1 plus 13 times +1 plus -1 minus 2. I think I get 7 minus 3. Check my arithmetic, but that's clearly not 0. Alright, so I don't have to do synthetic division with 1 or negative 1. How about 2? I need 6 times 2 cubed plus 13 times 2 squared plus 2 minus 2. That's not looking good. 6 times 8, 48. 13 times 4, and that 52 plus, oh wow, we're just way off. That's definitely not 0. Okay. So it looks like we may end up with just not integer zeros, but these fractions as one of the zeros. Let's hope negative 2 works. 6 times negative 2 cubed plus 13 times negative 2 squared plus negative 2 minus 2 more. Negative 48, plus 52 minus 2 is a total of negative 4, 0. All right. So the video's gotten pretty long, so let me just put a summary here. My polynomial will factor. Since negative 2 is a 0 by the factor theorem, x plus 2 is a factor, and I'll leave it to you to figure out what this quadratic would be. But all the zeros, just so you can check this on your own, not only was negative 2 a 0, but if I look over at my answers, it looks like negative 1/2 and positive 1/3 would have been zeros as well. Okay, good luck with your factoring.